Hi and welcome again to this course on space vehicles and orbital dynamics. In this video, we are going to cover the second part of the two-body problem. We will take off from where we left in the previous video. So we had analyzed the conservation of mechanical energy, angular momentum vector, and eccentricity vector. Here, we're going to start by looking at the equation of the trajectory in the two-body problem. So this equation will allow us to write the position vector of the smaller particle in the two-body problem in cylindrical coordinates. In other words, we will be able to write something like this, the radius as a function of the angle. This will not allow us yet to determine what is the time dependency of the position vector and the velocity vector. This will have to wait until the next video. Next, we will take a look at the three different types of orbits that we will have in the two-body problem. These correspond with the three types of conics that we analyzed in the last video. So we have elliptic orbits, parabolic trajectories, and hyperbolic trajectories. Next, we will dedicate our attention to the velocity vector in the two-body problem. So we will rework the energy equation to obtain an expression that is quite useful, the Viva equation, which is just the energy equation where we determine the value of the energy constant as a function of the semi-major axis of the two-body problem. And from there, we will get some important characteristic velocities of the problem. After that, we will continue to look at the velocity vector. Okay, so we will see the vector nature of this velocity. And to close the lecture, we will look at some particular reference frames, and we will introduce also the classical orbital elements. In order to derive the trajectory equation, our starting point will be the equation for the two-body problem as we have obtained last time. Now, the best way to obtain the trajectory equation is perhaps to project this equation in the cylindrical vector basis. All right, so we have the vectors ER and E theta. Remember that the position vector in cylindrical coordinates can be expressed in the following way, using the vector ER. Now, if we take derivatives here and we pay attention to the fact that ER is not a constant vector, but it depends on theta, we have to write it as follows. So we have this on the one hand and this on the other, E theta. Okay, now if we take another step of derivation, the acceleration can be expressed as r second minus r theta dot square ER. Okay, the second term comes from taking derivatives in E theta in the second term of the velocity, plus r theta second plus 2 times r dot theta dot in the direction of E theta. Okay, so when we project in the ER and E theta directions, the equation of motion reads like this. Let us start with the last one, the equation in the direction of E theta. This equation is integrable if you multiply by r. Okay, so as soon as you multiply by r, you can see that what you have is the exact derivative of r squared theta dot. All right, so this is nothing else than the magnitude of the angular momentum vector that we have found before, expressed in cylindrical coordinates. So this is nothing new. This is something that we already knew. All right, here we recover it from the azimuthal equation of motion. Now, what really is important for us in order to obtain the trajectory equation is the equation along ER. So in order to progress in this direction, we have to do some mathematical work first. So we are going to try to eliminate time from this equation. So you see that we have derivatives with respect to time, and we are going to do the following. So you see that we have, first of all, we have a theta dot square here. In order to eliminate theta dot, we can use the expression from the angular momentum magnitude, and we can replace every instance of theta dot that we will find as h divided by r squared. Okay. Now, for the derivatives of r with respect to time, we can do the following. So we start here with r dot, which is just the derivative of r with respect to time, and we change variables into theta. Okay, so we can rewrite this time derivative just like this. Now we find again a theta dot, which we can replace with h over r squared. Okay, and finally now we have r squared on the denominator times the derivative of r in the direction theta, which we can summarize as the derivative of minus 1 over r. You can check indeed that if you go backwards, you recover this result. By taking one additional step of derivation in time, we can find what is our double dot, okay, our second. And this is what we find. So basically, we have this derivative of time, which again, we replace as a derivative of theta, okay, using the same trick as before. So the derivative in time is equal to theta dot d theta. And again, we replace this theta dot that appears with our h over r squared. And this is what we get. Okay. So now, if we replace these terms into the equation of motion in the direction of r, our equation starts to look like this. And it may seem that we have not done any progress, but actually, this is an equation that we can clean a lot. Okay, so here I have divided by h squared and multiplied by r squared in order to remove most of the terms that appear in that equation. So here you can probably start to identify something familiar. You see, if we look at these parentheses that appear here as a single variable, perhaps we can give it a name, for example, u. What we have is, in essence, an equation that looks like this. The second derivative of u in the independent variable theta plus u equals some constant. Now, this is an easy differential equation. This is actually the equation of a forced harmonic oscillator with frequency equal to 1. And we can integrate it right away. We know the answer for this. Okay, so our solution for u, which is 1 over r, can be expressed as you can see over here. This would be the solution to the homogeneous equation, and this one multiplied by mu h squared is the solution, the particular solution to the forced equation. And we have two integration constants, so we have this e here and this theta 0, which depend on initial conditions, of course. Now we can actually choose whatever value for theta 0 we want, as long as we choose our origin for theta, the reference for theta, in the appropriate way. So without loss of generality, we can make theta dot equal to 0. If we solve for r, we finally obtain this expression, which is the equation that we were looking for. This is the expression of r as a function of theta, and it is therefore the equation of the trajectory. Now, by examining this expression, we can find, by comparing with known relations, that this is the equation of a conic section in polar coordinates with the origin at one of the foci of the conic section. And this is actually, therefore, an equation that looks like this: p plus e cosine theta. Okay, so we, by analogy, we identify the numerator here with the parameter of the conic, okay, p, the semilatus rectum, and the e that we had introduced before as an integration constant, we see that it is actually the eccentricity of the orbit. Okay, so we had already given that name intentionally. So this is therefore a demonstration that the first law of Kepler is true. The conic sections are the solutions to the trajectory in the two-body problem. Okay, actually, Kepler's law established that all the planets have elliptic orbits. We see here that elliptic orbits are not the only possibility in the two-body problem. We may also have parabolas and hyperbolas, which are also conic sections. So this allows us to find this important relation between the geometry of the orbit, which is here represented by the parameter p, and the energetics and the kinetics of the motion, which relate the angular momentum magnitude and the gravitational parameter. Okay, this relation is very useful for many computations. Now, the expression that we have here is in polar coordinates. Of course, we can go back to Cartesian coordinates. We just have to multiply this by cosine and sine, and we get x and y, as you can see over here. A different but faster route to the trajectory equation is to use the eccentricity vector that we introduced on the last video. So remember that this is a vector that is a constant of motion. So if we dot multiply this definition by r, we obtain the equation that you see over here. Clearly, this simplifies, and we have introduced the angle theta as the angle between the e vector and the r vector. Okay, so well, clearly we are going in the direction of cylindrical coordinates here, and we are choosing the eccentricity vector as our reference for the azimuthal angle. So theta will actually be the angle from the pericenter. Now, the first term that appears here on the left-hand side can be simplified. So this is basically a mixed product, a dot product and a cross product together. So we can rearrange it, and we can write it like this. And by definition, this is just h vector. So we have h squared. So rearranging this equation and solving for r, you end up with the same result as before. Okay, so different way to obtain the trajectory equation. Now, to conclude this first part of this lecture, I wanted to make some final remarks about the trajectory equation. So observe that the result that we have obtained is not only valid for elliptic orbits, it's actually valid for the three different types of conic sections that we know that are possible solutions of the two-body problem. So not only elliptic, but also parabolic and hyperbolic cases are covered in this formula. The angle theta that we have introduced in this definition, in this formula, is the polar angle or the cylindrical coordinates angle. And it can be called the azimuthal angle, but in orbital dynamics, it's actually called the true anomaly. Okay, and you will see in this lecture and in following lectures that there are many different types of anomalies that we use in orbital dynamics. The word anomaly is a synonym to an angle. Okay, so an anomaly is an angular variable, nothing else, nothing more. In many texts and in some of the figures that we are using in these slides, instead of using the symbol theta for the true anomaly, we use instead the symbol nu. Okay, so don't be surprised if you see nu in some of the diagrams. Well, finally, and as I was saying before, this result that we have obtained, the trajectory equation, proves the first law of Kepler. Okay, we see that indeed planets have elliptical orbits, and these correspond to this equation for values of the eccentricity smaller than 1. And in fact, we see that there are other solutions for the two-body problem. The parabolic and the hyperbolic cases are also valid solutions. In this and in the following slides, we are going to take a closer look at the different types of conic sections, which are the solutions of the trajectory equation. So starting with the elliptic case, I wanted to start by showing you geometrical construction that you may not know and which is extremely useful for things that we are going to see in the next lecture. So starting with this ellipse over here, given any ellipse like this one, we always can define an auxiliary circle which has as radius the semi-major axis of the ellipse. So this circle is tangent at the vertices of the ellipse, as you can see over here. Now, this distance here is b, the semi-minor axis of the ellipse. So we can find that there is a one-to-one correspondence between every point on the ellipse and a point on the circle. Okay, basically we take a vertical line and we project or we displace the point of the ellipse against the corresponding point on the circle. And there is a very simple transformation for the coordinates of this point. Okay, so imagine that we call this point P and this point P prime. Now the x coordinate of P is the same as the x prime coordinate of P prime, and the y coordinate satisfies this relation. The ratio of y prime divided by y is equal to the ratio between a and b, which are the values involved in the definition of the ellipse and the auxiliary circle. So this auxiliary circle is very useful for solving a number of things, but in particular it allows us to parameterize our ellipse in a different way than using the true anomaly that we had introduced before. Remember that the true anomaly is the polar angle taken from the active focus of the ellipse. Okay, so this angle basically. In fact, it turns out that we can define a different angular variable which allows us to represent every point in the ellipse and has some advantages. So this is what we are going to call the eccentric anomaly, as you can see over here. And it is the angle defined as follows. So instead of measuring from the focus of the conic, we move to the center of the conic. And we take the angle from the horizontal axis, not to the point where we are interested on the ellipse, but to the corresponding point on the auxiliary circle. And the angle that we have here is what we call the eccentric anomaly. Observe that we are using this correspondence between points in the ellipse and the auxiliary circle. So for a given point B, as shown here, we first find the B prime point on the auxiliary circle, and then we have the angle, which is the eccentric anomaly. Now, it is possible to find trigonometric relations between theta and E. And we will actually learn how to derive these expressions in the following video. For now, let me just give them as a result over here. Okay, so these are the relations that allow you to go from eccentric anomaly to true anomaly and vice versa. Regarding the elliptic case, remember that these values are always satisfied for ellipses. So the semi-major axis is a positive finite number. The eccentricity is smaller than 1, and the energy of the ellipse is smaller than 0. So it's a negative value. Using the eccentric anomaly that we have just defined, it is possible to recast the expression of the trajectory, and it actually looks a little bit simpler. It looks like this. Okay, so you see that as we vary the value of E, we have a constant part. Okay, so basically the first part of this equation corresponds to a circle of a constant radius a, and the second part is a variable term, which is a sinusoidal term, a cosinusoidal term, that goes with the eccentric anomaly. And this allows us to represent an ellipse not from the focus but from the center using this eccentric anomaly. Of course, you can always try to find the Cartesian coordinates associated to r and theta and express the result in terms of E, and those are the results that you see over here. Okay, so those are the expressions of x and y of the ellipse in terms of the eccentric anomaly. And moreover, you can also eliminate completely the parameter and have an implicit form for the ellipse in terms of A, B, and E, as you see over there. Elliptic orbits are the only closed orbits that we have in the two-body problem. So associated to them, it is possible to find an expression for the period of the orbit. In order to compute this expression, we are going to use the result that we found the previous day, which relates the area rate that the radio vector sweeps over time with the angular momentum magnitude. Remember that to obtain this result, we have to draw a differential area. It's basically a small triangle, a differential triangle, swept by the radio vector between two instants of time, and we then relate this with the angular momentum vector magnitude. So you have this expression, and basically what you have here is a differential equation that you can integrate over the full area of the ellipse. And if you do that, then, well, you will find an expression for the time it takes the object to run a full ellipse. So from geometry, we remember that the area of an ellipse is given by this expression. Observe that if A and B are equal, that is in the circular case, the formula resolves into the well-known formula for a circle, which is pi r squared. Yeah. So, well, this is the formula for the area of an ellipse. So if we integrate this differential equation for one full orbit, on the left-hand side, we will have the full area of the ellipse, which corresponds with this value. And on the right-hand side, we will have the period, which we are going to call tau. Okay, so rearranging this equation, we can write it as you see over here. Now, the result that we get can be left in this form, But actually, we don't like using b in our expressions, so instead we are going to replace b in terms of a and e using this formula. And moreover, we can further replace this in terms of the semilatus rectum and finally in terms of the angular momentum magnitude. All right, remember that this is an extremely useful expression that relates the dynamics of the two-body problem with the geometry of conic sections. Okay, so once we have used these expressions and we enter the result here to eliminate b, we finally can express the period of the orbit like you see over here. So this is a quite fundamental result, and it reveals something interesting. If we square this expression, we find that the period square goes like the semi-major axis of the orbit to the third power. Now, this is essentially what the third law of Kepler states. So we have proved also the third law of Kepler from the mathematical framework of Newtonian mechanics, just by integrating this small differential equation over here. And by the way, this relation for the period is what we use sometimes to identify what is the gravitational parameter of some celestial bodies of which we don't know the mass. For example, imagine a small asteroid and we have a space probe orbiting this small asteroid. Well, we can count what is the time that our small spacecraft takes to orbit the asteroid, and from there, using this formula, knowing the distance at which we are orbiting from the asteroid center, we can estimate the value of the gravitational parameter, which is an indirect measure of the mass of that object. Finally, associated to the orbital period in the elliptic case, we also can define a mean angular rate. The mean angular rate is just the inverse of the period multiplied by 2 pi, and it can be understood as the mean angular rate at which the object is rotating in the orbit, is going around in the orbit. Okay, so it doesn't represent the angular rate at any specific time. It's sort of an average value for the full orbit. Moving on to the parabolic case, as we have advanced already, the parabola is just a transition case between the elliptic orbits and the hyperbolic trajectories. So it's basically the case of the eccentricity exactly equal to 1. So it's very hard to reproduce in practice. We are either in a very elliptic case or a slightly hyperbolic case in practice. In any case, the parabolic case is of interest because it is the lowest energy trajectory that allows us to escape to infinity. Okay, so it is the trajectory that has eccentricity equal to 1 and semi-major axis equal to infinity. Now, since we don't like working with this because this is not really representing what is the size of our parabola, instead we use a parameter that is well posed, which is the semilatus rectum. Okay, so the semilatus rectum, or the parameter of the orbit, is always a finite value and a positive value. So in cases that are close to parabolic, we tend to use p instead of a to represent the size of the orbit. The parabola also has zero energy, and this is important because it is related with what we just said over here, the fact that we can go to infinity with this trajectory. Now, if we remember from our energy equation, okay, this is he, you can see that the only way that we can go to infinity, so when this r goes to infinity, this term over here vanishes, all right? So the only way that that can work out, because this is just always a positive number, it is a square number, so this only works out if the left-hand side in this equation is smaller or greater or equal to 0. All right, so 0 is the smallest possible energy with which we can reach infinity. Now, a parabola has a radius of the pericenter that can be expressed in terms of the parameter as you see over here. Okay, so just half of the parameter, the semilatus rectum. And associated to the parabola, there is an important velocity, as we will also see later, which is called the escape velocity. The escape velocity is the velocity that you obtain when you solve this equation for v. Okay, so assuming that the energy is 0, the case for the parabola, you can find this expression for the velocity at each point of the parabola. And indeed, this is the magnitude of the velocity regardless. This expression it satisfies that it is the magnitude of the velocity at each point of the parabola regardless of where we are. Okay, so it's always true, and of course it's a function of r. This velocity is important because if we want to escape to infinity, we must make sure that regardless of our distance to the center of the planet, we have a velocity of this magnitude. As long as that is true, we will enter a parabola and then we can escape. Velocities greater than this one also allow us to escape, but then we will not be in a parabola, we will actually be in an hyperbola, as you will see later on. When you take the limit of r going to infinity in this equation, you will immediately find that v goes to 0. And this is also relevant. A parabola trajectory allows us to go to infinity, but we will reach infinity with a 0 velocity. So as we approach infinity, the velocity goes to 0. Well, finally, to conclude this small discussion of the parabola, this is the expression that we can use for the parabola in Cartesian coordinates. Finally, in the hyperbolic case, the body has more energy than the minimum necessary to reach infinity. That is, it is more energetic than the parabolic trajectory. The hyperbola has a negative semi-major axis, an eccentricity that is greater than 1, and as we have just said, energy, a mechanical energy that is greater than 0. So the fact that this is greater than 0 means that as r goes to infinity, the final value of the velocity that you find is greater than 0, and that is what we call the hyperbolic excess velocity. So it can be computed directly from the mechanical energy equation just by making r go to infinity, and this is the result that you get. In an hyperbola, we have asymptotes, which is something that a parabola doesn't have, and there is a very simple way to compute the angle of these asymptotes. So if you use the equation of the trajectory, you can take a look at the denominator and take the condition that the denominator goes to 0. That is what makes r to go to infinity. So from there, you immediately find the value of the true anomaly for which the asymptotes take place. And actually, that is this angle here. Okay, so the angle that will take the position of the particle when it goes to infinity along the direction of the asymptote. Now, when we describe the asymptotes of an hyperbola, usually we don't use theta infinity, but instead we use the complementary angle beta that you can see over here. Okay, so this is actually the supplementary angle, 180 degrees minus the theta infinity give you the value of theta of beta. All right. Another important angle associated to this is the so-called turning angle of the hyperbola. And this is relevant because imagine that you have a spacecraft that is approaching, for example, Jupiter, say with this incoming hyperbola. This is something that we will see later in this course. After the close approach to Jupiter, eventually the spacecraft will leave again the domains of Jupiter and its velocity will have changed. The velocity vector will have been rotated. And the rotation angle or the turning angle is actually this delta angle here, all right, which is related, of course, with beta and theta infinity, as you can see over here. Another relevant number associated to hyperbolas is the so-called impact parameter. The impact parameter is this distance, the separation of the asymptotes with the focus. Okay, so it is the same one for this other one, of course. This distance is b, and it's actually the same as the magnitude of the semi-minor axis of the hyperbola. Okay, I use the absolute value of b, as you can see over here, because depending on the definition of b that you take, it is an imaginary number. And finally, for the Cartesian representation of hyperbolas, there are many ways that we can do it, but this is the implicit form. You can see that it is in essence the same one as in the case of the ellipse, except for this minus sign over here. All right, the next thing that we are going to discuss is the vis-viva equation. So this is, in essence, the equation of the mechanical energy that we already know, but when we compute the actual value of he, this constant, in terms of the parameters of the conic, that's when we call this the vis-viva equation. So there is a very simple way to compute the value of the mechanical energy of our body. Perhaps the simplest way is to take a look at what happens at the pericenter. And of course, you can do the same thing at the apocenter if this is a elliptic orbit. But in any case, the pericenter works fine. So remember that the radius of the pericenter can be computed in this way in relation with A and E. And since the velocity times r times the velocity is h, and at the pericenter of the orbit, you have that the radius and the velocity are orthogonal, okay, you can write that RV is equal to h, the magnitude of these vectors. All right, this happens at the pericenter and also at the apocenter of elliptic orbits, but these are the only points where the velocity and the position vector are strictly orthogonal. So using the fact that at the pericenter this is true, okay, and sorry because we don't need a subindex for the angular momentum, we can have a very simple formula for the velocity. All right, so once we have that, we can also replace h in terms of p or a and e, as you know, with the famous formula that relates the geometry with the dynamics of the two-body problem. We can replace these values in the energy equation, and this is what we get. Okay, so in order to simplify this a little bit, observe that here in the numerator we have this 1 minus e squared, which we can write as 1 minus e, 1 plus e, and then we can simplify one of these parentheses with a negative number. All right, so when you do that and when you combine these two matrices, eventually all that remains is a very simple fraction. Okay, so minus mu divided by 2a. When a is positive, clearly the energy is negative, which is the case for the ellipse, so it makes sense. And when a is negative, the case for the hyperbola, the energy is positive. When a goes to infinity, the case of the parabola, the limit case of the parabola, the energy is equal to 0. One of the interesting things of this formula is that it shows that the mechanical energy depends only on the semi-major axis. There is no dependency whatsoever on the eccentricity of the orbit. All right. So now that you can find this, you have found this value for he, you can replace it in the equation of energy and you get this very useful expression. Now that we have the vis-viva equation and we know that the mechanical energy is minus mu over 2a, we can use the equation of the mechanical energy, the vis-viva equation, to solve for the velocity. And this is what we find. So we can apply this equation to different situations and find some characteristic velocities of our orbits which are quite relevant. For example, if we have an elliptic orbit and we particularize this expression at the pericenter, where remember we have that expression for the radius, okay, or at the apocenter, we can find the velocity at the pericenter and the apocenter, as you can see over here. Observe that the expressions are very similar. We just have to swap the pluses and the minuses. And observe also that the velocity at the pericenter is greater than the velocity at the apocenter. Okay, and that actually makes sense because in your orbit you have a smaller radius at the pericenter, okay, and a larger radius at the apocenter. And since h at these points where the position and the velocity vector are orthogonal is equal to r times v, okay, then this means that the velocity here has to be much larger than the velocity here. All right, so this makes sense with this expectation. Another application of this formula for the velocity is in the case of a circular orbit, where the radius is just equal to a at all points of the orbit. And when we apply that condition, we get this very simple expression. This is the velocity, the circular velocity actually is called, of a circular orbit. And you see that it decreases with altitude. The farther up that we are, the lower the velocity magnitude. We can do the same thing by setting the mechanical energy equal to 0 or the semi-major axis going to infinity, which, as we know, that's the case for a parabolic trajectory. And as expected, what we get in that case is the escape velocity that we have introduced already. Observe that it has the same form as the circular velocity, except that it has the 2 inside of the square root. And finally, if we focus on the case of a hyperbolic orbit where the mechanical energy is positive and the semi-major axis is negative, we can compute the value of the velocity at infinity, and that is the already introduced hyperbolic excess velocity. To complete the discussion of the velocity in the two-body problem, we are going to look at the components of the velocity vector. So in order to get them, one thing that we can do is to work with the expression of the trajectory equation. So if we take derivatives in time in this expression, we know that theta is a function of time, we can get what is known as the radial velocity or the radial rate. So after some algebra, we can write this derivative as you can see over here. And moreover, this can be simplified a little bit more in order to get the expression that you can see here on the right. So this expression reveals that the radial rate has a 0 when theta is equal to 0 or 180 degrees. And that makes sense. The radial rate is the variation of the length of the radius, of course, and that variation is 0 at the vertices of the conic, where it passes from decreasing to increasing and from increasing to decreasing again. In order to get an expression of the azimuthal velocity, we have to work with the expression of h. Okay, so remember that h can be written as r squared theta dot. All right, so the azimuthal velocity is r times theta dot, and therefore it's just the ratio between h and r. So here you again can see that the smaller r is, the larger the azimuthal velocity, and vice versa. The larger the radius, the smaller the azimuthal velocity. By expanding the value of r, again using the expression of the trajectory, you can write this velocity component in this form. Now, particularly interesting variable is the flight path angle of the body, and that's just the angle formed by the velocity vector with respect to the local horizontal. So if this is the local vertical, at 90 degrees you have the local horizontal, and the angle of the velocity with the local horizontal is what we call gamma, positive in the sense of the figure. So we just have to take the ratio between VR, okay, the component in the vertical, and V theta, the component in the azimuthal direction, in the local horizontal, and that gives us the tangent of this angle. So that's an expression for the flight path angle that you can use. The flight path angle is positive in the first half of the orbit if it's an elliptic orbit, and negative in the lower part. All right, one additional thing that we can do with the velocity is, instead of working in cylindrical components, as in here, we can project back to the Cartesian reference frame, the Cartesian vector basis, and obtain Vx and Vy, as you can see over here. And in fact, there is an interesting result that you can find quite easily if you take a look at the expression of these components. You can see that there is a rotating term of the velocity of amplitude mu over h, and a component that is constant in the direction of vi, which is mu divided by h multiplied by e. So let me clean this a little bit so you can see this drawing better. Actually, we can write the velocity vector in this interesting form as a constant vector which has a constant direction and a constant magnitude, and a vector that has constant magnitude but rotates with the value of theta. Okay, so this is the azimuthal unit vector in the azimuthal vector basis. So indeed, if you try to plot the velocity vector at different points in the orbit, you can see that it is always the construction of the sum of these two vectors, one which is fixed and the other one which rotates depending on where you are. So here in orange, I have represented the second part of this expression, okay, the constant one. You see that it's always pointing up along the j direction, and the first component here is represented in green. Okay, so for an elliptic orbit, since here we have the centricity, which is a value that is smaller than 1, the first component is larger than the second. And we can see that when theta is equal to 0, both of them point in the same direction, so they add up, therefore giving a larger magnitude of the velocity at the pericenter. When we are at the apocenter, the vectors go in the opposite direction. So actually you have a small velocity pointing down due to the green vector being larger than the orange one. At any other point of the orbit, you have them at different angles, and in order to find the velocity vector, well, you would have to do the vector addition. For example, at this point, you would have a vector that goes like this. Remember, of course, that the velocity vector, the sum of these two partial components, the velocity vector always is parallel to the trajectory. Okay. Now that we have the velocity components in cylindrical coordinates, as we have seen before, we can do something interesting. We can try to create a diagram of velocity space. This is called the autograph. Okay, so basically we are going to plot the radial rate versus the azimuthal velocity, as you can see over here. And since everything is parameterized as a function of theta, we can vary the value of theta and see what type of figure we get in this velocity diagram. And the result that we get is a circle with an origin that is displaced from the origin. The value of the displacement of the origin is in the direction of v theta, and you can see that it's just this constant value. Okay, so for example, in the first diagram, which corresponds with the case of an ellipse, you have the circle with the center positioned there. The radius of the ellipse corresponds, so the radius of the circle corresponds then with mu over h times e, okay, which is also the value that you get over here after multiplying. So the pericenter is found when theta is equal to 0, and that gives you the maximum value of the velocity. At that point, all the velocity is in the azimuthal direction, and the radial rate is equal to 0. As you increase the value of theta in this diagram, you will move in this direction. So the azimuthal velocity decreases and the radial velocity increases. At the apocenter, you reach this point that gives you the minimum velocity, and again, all the velocity is in the azimuthal direction. This diagram also shows you what is the value of gamma, the flight path angle. Okay, so remember that the gamma is the ratio, or the tangent of gamma is the ratio between the radial velocity and the azimuthal velocity. So here you have the triangle that gives you the value of gamma. In the case of the ellipse, you see that the circle gives you the full orbit, and actually you have a positive value of the azimuthal velocity for all the points. All right. In the case of the parabola, you see that you again have a circle, but in this case, it is tangent to the origin. All right. Well, this is interesting and has the following interpretation. This is again the pericenter of your trajectory, the pericenter of the parabola. As you move farther and farther away, your velocity decreases and decreases until it eventually reaches the value of 0. This is actually when you reach infinity. Okay, so you will never, you will have to wait for an infinite amount of time to actually get there. But this is the figure of the full autograph in the case of the parabola. In the case of the parabola, the flight path angle also has a very interesting relation with theta. Now, since this is the center angle from the circle, and this angle begins on the border of the circle, we know that we have this relation. The central angle is twice as much as the angle from this edge. All right. So for the parabola, this is a relation that holds true all the time. The flight path angle is half the value of the true anomaly. And finally, in the case of the hyperbola, the center of your circle is actually in this way. So the circle intersects with the horizontal axis, and the intersections with the horizontal axis give you the position of the asymptotes. Okay, so those asymptotes are associated with this value of the true anomaly, okay, as we have seen before, and here in this diagram they also show again. In the next part of this video, I want to talk to you about some important reference frames. To start with, I want to introduce two types or flavors of Earth-centered reference frames, of which there are many. First of all, we have the so-called Earth-centered inertial or ESI reference frames, which in essence are centered on the Earth, but they are not rotating. So the axes point in fixed directions of the sky. While in reality this is not truly an inertial reference frame because the Earth is rotating about the Sun and so on, for most practical purposes we can treat this as an inertial reference frame. There are many types of Earth-centered inertial reference frames, but the most useful ones are those where the I and J axes are contained in the equatorial reference frame. Another type of Earth-centered reference frame is the Earth-centered Earth-fixed reference frame, or SF, which is rotating with the Earth. Okay, so as the Earth rotates eastward about the north-south axis of the Earth, this reference frame is moving with the surface of the Earth. So an observer on the surface of the Earth, on the ground, is basically moving with this type of reference frame. Now, clearly, this is a non-inertial frame, okay, because it is rotating. Just as we have done for the Earth, we can do with other celestial bodies such as Mars or the Sun. So we can define a Sun-centered inertial and a Sun-centered, Sun-fixed reference frame, and so on. A particular type of Earth-centered inertial reference frame is the perifocal reference frame. The only peculiarity of this reference frame is the direction of the vectors of its basis. So we are choosing the I and J vectors to be contained in the plane of the orbit that we are studying. And the first vector, the I vector, always points in the direction of the pericenter. So we can use the eccentricity vector to find it, just normalizing it. The K vector points in the direction of the angular momentum vector. So it's always perpendicular to the orbital plane and oriented such that the body in the orbit rotates according to the right-hand side rule. And finally, the J vector follows from this cross product and it points in this direction, as you can see in the diagram. So in this case, the body is moving in this direction. All right, finally, we can also talk about the celestial sphere. The celestial sphere is just in the case of an Earth-centered inertial reference frame, is when we choose spherical coordinates to describe the position of anything in the sky. So these spherical coordinates, we can call them rho for the radius, alpha for the first angle, and delta for the second angle. And in the context of the celestial sphere, these are usually called range, right ascension, and declination. Okay. Well, it really depends on which Earth-centered inertial reference frame you choose to define your spherical coordinates. This is usually a Earth-centered inertial reference frame which does not use the equator, but instead uses the plane of the ecliptic to compute these spherical coordinates. We will see later on in the course about these details. Finally, when we talk about the celestial sphere, usually we just ignore the value of the radius, okay, the range of the position of the objects in the sky. So we can just take rho equal to 1, for example. And this basically projects all the objects in the sky to the unit sphere, right? The final topic for today is the classical orbital elements. So this is something that we have to discuss in the context of the different ways that we have to express where a satellite is, or any object in the sky is, and how it is moving. So that, in other words, means how we can relate the state of an object in the sky. So there are different ways. One is the state vector, as you see over here, which is just a 6-dimensional vector that concatenates the position and the velocity vectors. So if you give me these 6 numbers, I will know exactly where the object is and how it is moving. So I have all the information about the state of the object. So this is actually a very practical representation in the context of some computer codes when we are trying to simulate orbits numerically, for example, but it lacks some interpretability. So if I just give you some numbers for R and V, it will be almost impossible for you to just, by looking at these numbers, to know if this is an elliptic orbit or a parabola or a hyperbola. So how can you get a better representation of your state in a way that is this more human understandable just by looking at the numbers? That is where classical orbital elements become an interesting choice. So classical orbital elements are an alternative to the state vector to represent the position and velocity of your body. They are called in many other names. They can also be called Keplerian elements. And in essence, what we do to define them is by working on an Earth-centered inertial reference frame, we define them in the following way. The first 2 classical orbital elements are numbers that you already know. So the first one is the semi-major axis of the orbit, and the second one is the eccentricity. These 2 classical orbital elements define the geometry of the orbit. The first one, the size, the second one, the shape or the type of the orbit. Now, regarding the semi-major axis, as we have seen with the derivation of the Visviva equation, it is univocally related with the energy of the orbit, but also with the period in the case of an ellipse. Okay, so either the semi-major axis or the energy or the period are alternative representations for this first classical orbital element. Near parabolic orbits, we know that A goes to infinity, so an additional alternative to give the first orbital element is to give the parameter of the orbit, the semi-latus rectum. So we know that this is always a positive number and finite, so it doesn't have any problem near parabolic orbits. Alternatively, we can also give the mean angular rate, which we have also defined. The eccentricity is related with the energy and the angular momentum, so you can compute it in many different ways. Of course, you can compute it as the magnitude of the eccentricity vector. You can also compute it from this expression over here, which is a function of the energy and the angular momentum magnitude, as I was just suggesting. The next 2 classical orbital elements allow us to identify the orientation or the attitude of the orbital plane. So starting with our reference plane here, okay, the plane, the horizontal plane made by I and j vectors, which is typically the equatorial plane, we want to somehow state how the plane of the orbit is oriented. Okay, so there are many ways to do that, but the way that is used in classical orbital elements is to involve the first 2 Euler angles. Okay, we will also use the third one later on. Now, the Euler angles that we are going to use are of the type 3, 1, 3. Okay, so the first rotation happens about the vertical axis. So that brings the initial axis, which are here. Okay, they are rotated into this auxiliary axis. Okay, and the angle of rotation over here is what we call capital omega. Now, this capital omega is named the right ascension of the ascending node, okay, or to make it shorter, RAN. This is the angle from this reference direction, which has to be stated in our definition of the SE reference frame, to the line of nodes. The line of nodes is the intersection of the orbital plane, okay, it's all this line that happens here, is the intersection of the orbital plane with the plane of the equator. Now, the second Euler angle allows us to tilt the orbital plane, so to bring it out of the equator by applying this second rotation. So this rotation will happen about this axis, okay, and it will bring this axis here to this position. All right, the rotation angle over here we will just call it I, and we call it the inclination. All right, so the inclination of the orbit is the angular distance between the two planes, the orbital plane and the plane of the equator. And usually it's given as an angle that goes from 0 to pi, right? If you have 0 pi, you have a plane that is equatorial because it coincides with the equator. If you have a plane that has an inclination of 90 degrees, you have a polar orbit. Anything that is less than 90 degrees will be a prograde orbit because, as seen from the North Pole, rotates in the counterclockwise direction. And if your inclination is higher than 90 degrees, the rotation as seen from the North Pole goes in the clockwise direction, so we call it a retrograde orbit. Now, the way that we can compute these angles is by taking dot products. So since we know that we have a vector that is always orthogonal to the plane of the orbit, one way to compute the inclination is to compute the dot product of that angle with k, which is a vector orthogonal to the plane of the equator. So the dot product can give you the cosine of the angle of the inclination. Similarly, in order to find the right ascension of the ascending node, the capital omega, we can play a trick. So the first thing that we want to identify is the vector n, which is this green vector here, all right, which is a vector contained in the line of nodes and actually pointing in the direction of the ascending node. By the way, we call it ascending node because it is the point in the orbit where the object crosses from the south hemisphere to the northern hemisphere. The one here on the back is the descending node because the object in the motion in its orbital motion crosses from the northern hemisphere to the southern hemisphere. So if we can compute this n vector, we can use the dot product with the I vector over here to find the cosine of capital omega. And similarly, we can also compute the sine of capital omega by dotting n with the j vector over here, okay, which is sometimes needed for disambiguating the quadrant of this angle. All right, so how can we compute the n vector? Now, the n vector is the intersection is in the intersection line between the equatorial plane and the orbital plane. So we can find this vector by taking the cross product between k and h. All right, so this is the way that you can compute n. Observe that we can spot a problem for a particular type of orbits. If the inclination is equal to 0, the orbital plane and the equatorial plane coincide. So the intersection between these two planes is just the full plane. There is not a line of nodes that we can clearly identify. So we cannot define omega in those cases. We say that the right ascension of the ascending node is undefined for equatorial orbits. The fifth orbital element allows us to orient the pericenter in the already located orbital plane. Okay, so the first two Euler angles, omega and I, allow us to identify where the orbital plane is, but we still have to identify where the pericenter is in this orbital plane. So the last rotation of the Euler angles, the third Euler angle, actually allows us to identify where this pericenter is located. So starting from the line of nodes, okay, from vector n that we have defined before, we will apply our third rotation until we find the pericenter of our orbit. This will be called small omega, okay, or argument of the periapsis, or pericenter is the same thing. Now, how can we compute this? You see, we always apply vector calculus to find these angles. So basically, if we want to find this angle, we need to use two vectors, the vector n, which we have already computed as the cross product between k and h, and a vector that points in the direction of the pericenter. Lucky for us, we know a vector that always points in the direction of the pericenter, which is the eccentricity vector. So if we compute it, we can find the cosine of small omega by taking this dot product. Okay. Again, sometimes it is necessary to disambiguate the value of omega, so it's usually necessary to take some additional steps to distinguish between positive and negative values of this angle, because the cosine of omega is an even function. Here we can also identify a second problem of classical orbital elements. What happens if our orbit is a circular orbit? Well, in that case, the pericenter is not a well-defined point because all the points along the orbit are identical. So we cannot define omega in circular orbital cases. To conclude this part of the classical orbital elements, observe that we have now the three Euler angles, okay, which again are of the type 3, 1, 3, according to the terminology that we usually employ for Euler angles. Now, finally, there is a sixth orbital element, and this is a value that we already know. This is the true anomaly, okay, which we will represent here with theta. Remember that sometimes it's represented with nu, and it is the angle that allows us to identify where the body is at a particular instant of time with respect to the pericenter. All right. So again, if you want to compute it, you can use the dot product of E dot R, and that will give you the cosine of theta. Again, in order to disambiguate it, you may need some additional calculations. And finally, we here find a third problem of classical orbital elements, which again tells us that in the case of circular orbits, since there is no clear pericenter, we can not define theta in a clean manner. We have to choose a direction, perhaps an arbitrary direction, but we cannot use the pericenter. So we also have that problem here. Now, the six classical orbital elements that we have introduced, which we'll repeat here, A, E, capital omega, I, small omega, and theta, are equivalent in the sense of that they provide the same information as the six numbers contained in the RV vector. Okay, so the state of our body can be completely determined by giving six parameters. This is one choice, this is another, but actually there are many other types of orbital elements. These are the classical ones. You can define many variations, and actually there are hundreds of them in the literature that you can use. Actually, being able to transform from R and V back and forward to the classical orbital elements is a very important skill, and we will develop it in the exercises of this week. So you will learn how you can go from here to here and vice versa. All right. The procedure I already advanced involves a lot of vector calculus. As you have seen, in order to determine all these angles, we need to use dot products and so on. Now, in this last slide, I want to talk about some special cases that are related with these undeterminations that we have with classical orbital elements. Okay, we have seen that there are two types of orbits that are problematic. On the one hand, we have circular orbits, and on the other one, we have equatorial orbits. And of course, we can have the both things at the same time, circular equatorial orbits. So these orbits are problematic in the sense that one or more of the classical orbital elements are not well defined, and we have to fix it somehow. Okay, and it is not only a problem of these orbits. Any orbit that is very close to circular or very close to equatorial will be very sensitive to variations in the conditions of the orbit, and those classical orbital elements will not be very well suited for studies of those orbits. Okay, so in those cases, we try to define alternative orbital elements to prevent numerical errors in the computations and so on. So let us focus first on the case of circular orbits, as you see over here. The main problem stems from the fact that there is no pericenter. Okay, so we cannot define neither omega, small omega, nor theta or nu. All right. So instead, one thing that we can do is to measure the angle from the line of nodes all the way to the position of the object. Okay, so that's basically the sum of these two angles, which we will call u, or argument of the latitude of the object. And while each of the angles individually is not well defined, the sum is. Okay. Observe also that in the case of circular orbits, the true anomaly is the same as the eccentric anomaly that we have defined for the ellipses, because the focus is the center and we are measuring angles from there. The orbit coincides with the auxiliary circle, is the same thing, so the two angles become the same thing. U can be computed in this case as the angle between the vector n for the line of nodes and the position r of the object. Finally, we also have equatorial orbits, okay, and in this case the problem arises because there is no well-defined line of nodes, so there is no ascending node. That means that we cannot define capital omega or small omega. All right. So instead, what we do is we define the sum of these two vectors, okay, so of these two angles, sorry, as the omega tilde true, which is the true longitude of the pericenter, okay, or the right ascension of the pericenter is the same thing. So again, each of the angles is not defined individually, but the sum is well defined, and we can work with that. Okay, finally, the combination of the two cases, circular equatorial orbits. In this case, we don't have capital omega, small omega, or theta well defined. So we need to solve it. And again, the approach is to just combine the three of them, which is well defined. So the sum of the three angles actually exists and is well defined. We will call it lambda true, and that is the true longitude of the object. Okay. So with these definitions, we have alternatives to the classical orbital elements specific for these pathologic cases. Okay. Observe that when we combine two angles, for example here, we go from 6 parameters down to 5. Okay, because we're actually just using 5 parameters. Same happens here when we define the true longitude of the periapsis, where we have 5. And in this case, actually, we have only 4 parameters. So what happens in these cases is that we are complementing our description of the orbit, of the state of the system, with the additional information that the orbit is either circular or equatorial or both things at the same time. So this replaces this missing parameter in our description. To conclude, observe that we can always define longitude of periapsis or this longitude of the object, even if the orbit is not circular or equatorial. We can always do this sum, okay? These sums. Of course, in this case, we are summing angles that are not on the same plane, so it's a bit strange, but it is sometimes done. So if you see it in some of the references, don't be afraid. It's just defined in this way. So that's it for today. In the next video, we will look at the problem of relating the position and velocity of the two-body problem with time by solving Kepler's equation. Thank you very much and see you next time.